This afternoon's presentation is hopefully going to be an interesting and educational one. We have with us Prof. Elvin from Wits, whose main focus is on, sorry, I've lost my bit now, but Alex does a lot of forensic work in structural failures, and his partner in this presentation, Emmanuel, is from the South African Institute of Steel Construction. Also has a fair bit of experience in forensics in terms of structural engineering, and they're going to present to us on failure analysis versus the design process. So I think we're going to get something interesting, not just on how to look at a failure, but where the differences might be between where we go wrong in designing something and what actually happens when it fails. I'll hand over to you now, Alex and Emmanuel. Thank you very much.
Yes, good afternoon. My name is Alex Elvin. I'm a professor at Wits University, a professor of structures. First of all, this is equivalent to lecturing into the void. So could you put up your hands on the Zoom call if you can hear me? So I'm just looking at the participants. If you can hear me, just put up your hands, please. Okay, excellent. So a lot of people can hear me, so we can then continue and start. So today's talk is going to be about failure analysis versus the design process. And the presenters will be myself and Emmanuel. Not only am I a professor of structures at Wits, School of Civil Engineering, but also director at Aura Entle Engineering and a consultant for Aura Engineering. Emmanuel Bromesco is the technical director of the Southern African Institute of Steel Construction. And I'd just like to point out that this presentation is copyrighted to myself and to Aura Engineering. So let us start off, and the rules for this presentation is if you would like to say something, you are welcome to jump in. You can just start talking over me. I'll stop and we'll listen, and then we'll have a debate. So feel free, this is your time as well as our time. If you have anything to say, we would really love to hear it. And as always, I prefer to have a backwards and forwards rather than just us talking and us talking and then us talking and then there's no response. So please feel free to jump in. So that's the rule. Those are the rules. We'll be talking about failure analysis versus design process. So let's see if I can start the presentation. The presentation will be divided into two main sections. The first section, let's call it theory, will be presented by me. We'll talk about collapse, we'll talk about failure, we'll talk about rational design, and then we're going to mix it all up and talk about everything at the same time. The second section will be the practical aspects, where we'll talk about failure and collapse from our experiences and from what has been happening in the news. As I say, if you feel that you want to ask a question, please feel free to ask a question, make a statement, flame me, whatever you want to do, go ahead. So as always, in my presentations, there will be a set of questions, and it's really up to you to participate or not to participate. I'll call them little quizzes. So the first quiz is coming up, and that is the first quiz, and I'd love you to vote. Question one. So let's pose question one to you. Who knows what a failure is? If you can just put up your hands if you think you know what a failure is, a structural failure that is, please put up your hands. Let's see who knows what a structural failure is. I'm seeing no hands, so please feel free. A few people have put up their hands. All right, a few more. All right. So quite a few people have put up their hands. You can put your hands down. Good. Maybe we should be listening to you if you think you know what a failure is. Question two, if you have a piece of paper next to you or you want to type it up so that we can all see, can you list the difference or the differences between collapse and failure? If you can just type it up and I'll read a few. I won't mention who wrote what. We just want to see. Could you tell me the difference between a collapse and a failure? Let me just scroll it up and down. Nobody's volunteering anything. Nobody's typing, nothing. Have we got a dead audience? Come. Difference between collapse and failure. Are we going to give up? Get you into the void.
There it is.
There's where?
In the chat.
I don't see it. Could you read it off? What did it say?
I'd say collapse a type of failure.
Excellent. All right.
Oh, there's quite a few actually.
Okay, read off. Can you guys hear Emmanuel talking? Where's the chat?
Down below.
Oh, yeah, I see
Yes.
the chat. Right. Let me just switch the chat on.
Failure, not considering something important.
Oh.
Failure is when yield stress is exceeded.
You better
Collapse.
global failure. Failure equals local. Collapse is when structures falls to the ground. Okay, good. All right. Okay. So let's see what I wrote.
Cool.
So a structural collapse is something that is obvious. A structural collapse is a failure. I agree with that. And a collapse can be global or a collapse can be local. The M1 temporary structure works that collapse. Let me try and click on the link. Sorry, let me go page up. Let me click on the link. And I don't know if you all remember, but about in 2015, the temporary works over the M1 collapsed at peak hour traffic. Unfortunately, several people died and many were injured. And what was surprising about this collapse is that there was absolutely no loading on the structure. When I'm saying no loading, I mean no useful loading, no live load. So the temporary works were not carrying any wet concrete or anything else. There was a little bit of wind, but that's what I consider a global collapse. The entire structure collapsed. All right. Now, we can classify failure in a more complicated way. There are service failures and there are ultimate limit state failures. So a service failure, examples of that would be cracks, which are non-structural, for example, in finishes. They're visible deflections or vibrations or requiring maintenance, excessive maintenance. So here's an example of a non-structural crack. This is a crack actually in my bathroom, my very bathroom upstairs in this very house I'm sitting in. And there is a crack that has progressed through the very expensive tiles. You can perhaps see it, perhaps you can't. And what has happened here is that the pipes that were buried into the concrete have cracked and we have leaking. And the question is, have we got cracked plumbing? So this is an example of a service failure, which is structural. It's due to structural failure, but it is not what most people will call the ultimate limit state failure or what most people will call failure. So this is a very expensive failure in the sense that now we have to go and either live with it or we have to go and fix it. If we have to fix it, we have to pull up all our tiles, we have to retile, we have to regrout, etc. So this is a very, very expensive failure, and it's a service type of failure. Visible deflections. Most people, when they see visible deflections, which might not be ultimate limit state failures, would freak most people out, especially if they were laymen or laywomen. And vibration, of course, renders the structure non-usable. I was involved in a structural failure where the floor in an office space was vibrating excessively. In fact, it vibrated so much that it made the occupants, the office workers, ill. It made them nauseous. So the main thing about service failures is that it requires repeated repair and it's expensive to fix. So now let me show you another example of a failure. Notice these are not collapses, right? Notice these are not collapses. These are failures of the structure, which are very important, but they are not obvious. So examples of ultimate limit state failures, not collapse, are structural cracks, plastification yielding, some people wrote about it, loss of stability, buckling, it could be local or global, And the worst case of such would be structural collapse. So here's an example of my neighbor's roof, right? This is my neighbor's roof. And the structural, if you pay very careful attention, can you see there's a little wave here? Can you see that? It's quite clear in the photo, right? So this is an example of the underlying structure, which are timber trusses, have lost stability. Either one or two of them have lost stability, or the entire set of timber trusses have lost stability. So what we conclude here is that structural failures are sometimes very subtle in nature. You can hardly see them. This is hardly seeable, right? Nobody would actually pay attention to this, but this is portending a very dangerous situation and unpleasant one. Right, let's continue on to the concept of deflections. Now, I mentioned to you that deflections is a serviceability limit state failure, or deflection is a serviceability failure. But if the deflection becomes very large, then it can flip from being a serviceability limit state into an ultimate limit state. So let me show you here a photo that Spencer Erling has provided me. And here you see a crawl beam. Can you see how that has deflected? It has lost stability. Not only that, because the structure is unbraced, the portal frames have all keeled over, as you can see here. And now we're going from an unsightly or perhaps even imperceivable deflection problem to a large deflection problem. So now we're going into the ultimate limit state. The crawl beam is now very dangerous. And there are a lot of details here that I'm not going to get into, but you can see how the serviceability limit state of deflection has now flipped into an ultimate limit state deflection. As another example, here is a suspended slab made of ribbon block, which is very popularly used in this country and in fact all over the world. Besides the mistakes of putting the ribs the wrong way around, you have a huge sag in this structure, huge sag. This photo does not show the scary aspect of this deflection. And here too, the deflection is so high that the serviceability limit state is now on the ultimate limit state. You can see the amount of deflection by this gap. Can you see this gap? This is a steel beam, and we don't know what the purpose of the steel beam is. The beam looks completely out of place and completely useless for this entire span, because maybe it solves this problem, but next door problem it does not solve. So this is excessive deflections where we start to flip from serviceability to ultimate limit state. Right, so now get ready for a little test or two, quiz as I call them. Let's talk about rational design. So modern method of design is the so-called rational design, which utilizes experience, in most part experience, which is based on the historically what works. So you would be a junior engineer, a senior engineer, or somewhere in between engineer. You would be designing things based on history, history as in terms of from prehistory, where in Carthage or in Rome, say, they were building 6-story apartments already, 2,500 years ago. So based on history, it's been handed from generation to generation, and that's what we roughly call experience. The second tool that we use are the building standards and building codes. So now some of the experience has been codified, some tests, laboratory tests, in situ tests, practical aspects have been codified, some in codes, some in standards, and that's a second item that we use in rational design. And the third item that we use in rational design is the analysis method and the modeling approach, which usually uses computers and computer software. All this is cooked together to produce drawings, which is our currency as engineers, structural engineers. Now, I just want to point out to you that experience, which is this point, has unfortunately been replaced by computer software. And this replacement of experience by computer software is exactly where the problem lies and exactly where failure and collapse originate from. Right, so now let's look at two examples, right? Just two examples to explain to you the concept of rational, or let me even give you a hint for the quiz that is coming up, irrational design. Here is a structure which is an escape, fire escape at Wits University, and zoomed in actually on the other side, but around this point, it looks like this. So you can see I-beams, you can see which way the strong axis is. We see beams, and if you look at it very carefully, you see the structure, which is a steel structure, serving and intending to serve as a fire escape. It is leaning on this building, which is a concrete building. So my first question is, does this pass rational design? And my second question is, has this failed? So let's have a vote. Let's have a look with voting hands. Who thinks that this structure passes rational design? Please put your hands up. If you think this would pass rational design, please put your hands up. It was built, I would say, about 2018 or so. So it's been around for a long time. Who says this structure passes rational design? Please put your hands up or chat. Somebody's asked serviceability service state. I don't care. I'm just asking if this has passed rational design. Who says yes? Please put up your hands. A few people have put up their hands. Some people have kept their hands up. Anybody else? All right, let's put our hands down. Hands are down. Excellent. Who says that the structure has failed? Please put up your hands. Has the structure failed? Please put up your hands. 3 people have put up. Can you tell me why it has failed? Why do you think it has failed? It's a fire escape. Is the street protected against fire? If not, it fails. Street is protected against fire. There's no fire in the street. It's a huge expanse. Anybody
Steel.
else? Sorry?
Steel.
Where does it say steel?
Is the steel protected against fire, he says?
I don't see that. Well, oh, sorry. So I'm zoomed out. Sorry, let me just zoom in. Why is it not catching? For some reason, this is not catching. My zoom is on the blink. It's a fire escape. Is the street protected?
Is the steel protected?
I would say a collapse is a type of, hang on, I'm getting there. Oh, zoom is, it's a fire, right. No, the steel is not protected against fire, and I'll go so far as to say because it's an outside structure, it doesn't need to be protected against fire. All right, so let's have a look at what I have on my slides. Right, so nobody has written that it's unbraced in the direction shown. So this happens to be an exam question that I set quite often, or used to set quite often, and most people do not pick up that the structure is portal framed in the wrong direction and it's unbraced in the weak direction, and therefore the entire structure does not pass rational design. Now, let's ask you, has it thus failed? Has the structure thus failed? Failure is not considered something important.
Not yet.
Emmanuel, can you read what it says at the bottom?
He says not yet.
Has not yet failed. Doesn't appear so. Not yet. Yes. Somebody says it's failed. Column orientation is questionable. That's correct. Prop added afterwards. No, prop has not been added afterwards. It is a fire escape. It's a steel prisoner. All right. Anybody else? Failed rational design. Correct. It has indeed failed rational design. So I'll ask you again, has the structure failed? Yes, it has failed. Yes, correct. The structure has failed. It has failed because it does not pass rational design. So now if we look at this structure, right? So this we have crunched through. Let's now crunch through this. Let me explain what you see here. Here you see a main beam, which has got many stiffness. You can see all those main stiffness on the main beam. And then you've got what looks like a major haunch Major haunch. Not only is it a haunch, it's also got a stiffener here to protect the web. Yes, failure does not mean collapse. It is still standing because it has not collapsed. Standing does not mean that it has collapsed. It does not mean that it has not failed. Most likely also fixed to brickwork. Yes, it is fixed to the concrete. But now we are talking about the second structure, this one. This one was the simpler one. Now let's talk about this one, shall we? Who says that this structure has failed? Please, sorry, has passed rational design. Please put up your hands. Does the structure pass rational design? Please put up your hands. Does not pass rational design. Oh, all right. Anybody else? Does this one pass rational design?
Okay, right.
No?
A lot of no's.
No, has not passed rational
Why
design.
not?
Okay? So has it failed? Has this one failed? Has this one failed? This structure, has it failed? Nobody's, yes, it's failed. Anybody else? No, it has not failed. Stiffness not following standard design, therefore failed. Haunch, too weak axis of column. Ah, that's very good.
Cool.
That goes good. Yet, yes, it failed. All right. Right. So let's see what I wrote here. Non-standard haunch, problem number 1, connecting to web of column. And how in the world are you going to model this? This is unmodelable by most people, and it would be a very difficult problem to solve. So if you were to ask me, this has not passed rational design. It has failed. It has failed because it has not passed rational design. All right, let's now go a bit down the rabbit hole. So let's look at reasons for failure. You know, in the construction industry, as I guess in many aspects of life, we like to find the reasons of why things fail. And whose fault is it anyway? So the first fault could lie with the structural design engineer for not designing at all, making mistakes of faulty designs, or lack of poor supervision of construction. Plastic hinge created. The plastic hinge created for the previous question is irrelevant, I'm afraid. All right, so structural designer could be whose fault it is. It could also be the fault of the contractor by using the wrong materials, using the wrong sequence of construction, but usually due to cutting corners or hiding problems or obfuscation. I think Emmanuel was going to talk to us a little bit about that. And then, of course, there is the overload during construction. The third person or group of people that could be at fault would be the owner or the client for things like overloading or misusing the structure, and some people call it abusing the structure. There could be lack or poor maintenance, and does not demand accountability, which is often the case in South Africa. In fact, in most cases in South Africa, the owner and the client does not demand accountability from the construction and the building team. And then finally, it could be the fault of the administrator, for example, no or poor project management, and no failure in communication. So broadly speaking, we have that the design is incorrect. The rational design is incorrect. And remember, the rational design is done all on paper, not in real life experiments. Design is done on paper, on the computer, whichever, but it's all virtual. We can call it virtual. That is the modern process of rational design. So the mistake could be here. It could also be built incorrectly. The mistake could be here. Or it could be used incorrectly. The mistake could be here. And the person or the group that connects all people or all groups in the construction process could have also failed. So the uniting of all the elements in the construction could be missing or faulty. And now I'd just like to also blame, fault lies with God. You see, act of God. What in Latin is called force majeure. Now, unfortunately, in recent times, there have been many failures, and oftentimes God, or the act of God, has been blamed. And I don't think that that is 100% fair. So why do I say that? The act of God is a valid and reasonable explanation for why a failure occurs. But the act of God can only be invoked if something completely undocumented, unprior history experience occurs. Something like, for example, if there were no terrorist activity and all of a sudden there's a terrorist bomb that blows out many columns. Or if there is a tornado of unparalleled magnitude, or if there's indeed a tornado or even an earthquake in a zone that has never ever been classified as a tornado or an earthquake zone. All other problems, and these are very rare events, very, very rare events. All other events are one of these, or a combination of these. Right, so let me just go through some notes and then we'll get on to a little bit more exciting stuff. There's a difference between the reason for failure and the cause of failure. Structural engineers, we design and build to code and use rational design. And if we do that, can say we've built structure using rational design, then structure should not fail. The structure should not fail if we proceed along the rational design route. Structural engineers are not trained or equipped to determine root cause of failure. In other words, perform instrumentation in the form of measuring using sensors and sensor networks, doing forensic engineering and failure analysis. Structures do not read nor obey building codes. I repeat, structures do not read nor obey building codes. If a structure collapses or if a structure fails, it does not mean that the structure has violated the code. So, I repeat, structural engineers design to code and failures should not occur. If a failure occurs this way, the structural engineer is not equipped to to perform failure analysis and forensic. Now, some structural engineers, a very small proportion, are trained in this direction, so of course they can. But in general, structural engineers designed to code, structure should not fail. If the structure does fail, then the structural engineer is not equipped to go the other way. This way, yes, the other way, no. So let's explore this a little bit further. Right, so now we get onto something that I've put together and I've been intending to put together for a long time, ever since I talked to a colleague and she told me one very important thing. She told me, but it works. And ever since that day, a few years ago, I've wanted to write a paper, but it works. And the paper will be titled, but it works, strength considerations. Okay, so but it works, strength considerations. There will also be a second paper and a third paper following on with the first few words, but it works. Right, so let's have a quick quiz. Which beam works? I'll give you beam 1, you can see it in chalk here, beam 2 and beam 3. There are 3 beams. Can you see? They're all loaded identically in 4-point bending. Here's the loading scheme. We have a distributor beam that splits the load equally onto a test specimen. Here's my test specimen 1, 2, and 3. Beam 1, beam 2, beam 3. Can anybody tell me or type away in chat which beam has failed and which beam works, or any other comment that you might want to write? Let's give you a few seconds. Which beam works? Could you tell me, please? All of them are supporting dead load, and all of them are supporting a little bit of live load. Now I want to know, perhaps that's a hint, which beam so-called works. Anybody? Silence. Don't be shy. Let's hear what somebody has to say. Aha. Your photos are rubbish. I agree, my photos are not very good. I'm notorious for producing rubbish photos. Anybody else? Maybe the person is asking, can I give them a few details? All works, the design, deflection, limits will tell. Oh, that's very advanced for me. Hang on, number 1 and number 2 works, beam 3 over deflecting. Your photos are rubbish. They all work in inverted commas. Number 2 works. Excellent. I'm so pleased. Anybody else? They all don't work. Karaba, can't tell without the loading and failure criteria. Karaba, very good, Karaba. Number 3 fails. Anybody else? What's the difference between the photos? Can't you see number 1, number 2, and number 3 written in chalk? Here, I'll show you. My eyes are very poor and my photo is even worse. 1, 2, and 3. Can you see? They're all different. So I'm not crooking you. It's straight up 3 different beams, which we took a long time to test. Number 3 fails. What's the difference between the photos? 3 is cracked. Oh, yeah. My goodness.
Good eyes.
All right. Good eyes. Photos are rubbish, but your eyes are good. Looks like number 3 is signs of failure, subject to limits. I don't understand. All right. But I understand 3 to you has failed. Anybody else? 1 has failed. Number 3 appears oversized for the load compared to all the beams. Let me also let the cat a little bit out of the bag. Cool. All 3 beams have identical concrete that were mixed on the same day and are identically dimensioned. The length, the cross-section, and the loading is identical. What are the beam section properties? We'll talk about that in a second. What are the beam section properties? My eyes have failed, obviously. Spans. The span is very small. The span is 1.5 meters. Have no idea which one works. Impossible to tell. Very good. Anybody else? Consensus has failed. All right, let's have a look. All right, consensus has failed. Now let me drop an atom bomb on you. Are you ready? So now I feel that the slides are going to get very, very confusing and very, very complicated. I'm sorry for this, but here we go. There's no way to tell by visual inspection which beam has failed and which beam has not. I think you have to be there. You don't have to be there. All the data is in front of you. Let's look further. Answer 2. Safest not to jump to conclusion, but it works. Remember, it looks like it's working. Visible deflection 0. It seems to be holding up, but we have no idea. So the statement, but it works, is a non-conservative, ultra-liberal statement. And it is jumping to conclusions. All 3 beams on the outside are identical, and loaded identically, with identical boundary conditions. So let's start to explore. Right, so somebody asked, and here's the answer. We're going to experiment on reinforced concrete beams because I would think that concrete beams, reinforced concrete beams are not plastic, right? They're made of a brittle material. Concrete is a brittle material. So let's explore our understanding of failure and let's explore the statement, but it works. So here we start off with the same photo of beam 1, which now I'm going to release the information to you that it's a balanced reinforced beam, and the reinforcement looks like this. These are my shear lengths, and I've got 3 bars at the bottom and 2 bars on top, and I've got my shear lengths over there. So my loading scheme is here. Here's my photo. Here's my schematic of the reinforcement inside the beam. And I will further tell you that it's balanced reinforced. In other words, the compression and the tension zones are just correct to match itself. And if I were to apply this load and measure this deflection and plot my load versus displacement, I'll get a graph like so. And here I have my place where I took my photo. So this photo was taken right at the 0 loading. So now you are more than there. We are showing you as if you had X-ray eyes or instrumentation, and we've instrumented this beam, and we give you the force deflection graph. All right. So far, everybody is with me? Yes? Thumbs up if you're with me. Thumbs up or hands up. Okay, hands up. Some people are with. Right. Some people are with. Excellent. So let's come back here and see what we've got. Quiz. Where has beam 1 failed? Or has it failed? Who says beam 1 has failed? This is the beam we're looking at. I've given you the load displacement graph. Here is the rubber sheet photograph. I apologize for the rubber sheet photograph. 4-point bending. Here's the reinforcement. Here's the load displacement. We've got a load. This is the graph. Who says that the beam one has failed? Hands up or comment. One person says it's failed. Fail. Hands up. Fail. Failed. Oh, there's a consensus. Not fail. Oh, why is the one person not failed? Fail. I'm just reading what it says. Failed. So everybody's saying failed. There's been one outlier saying not failed. Anybody else? Failed. Deflection limit exceed to code. No, it hasn't. Wasn't the purpose to load it to failure? I've no idea. I've come into the lab. What criteria is considered? What criteria is considered to be failure? Excellent question. But you set your own criteria. We design for failure. We do not, nobody designs to failure, by the way. What criteria is considered to be failure? That's up to the engineer and the client to decide. Anybody else? I've given you the force deflection graph, and I've asked you if this has failed. And most people have said failed. Some people, through my line of questioning, are asking what is failure, blah, 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 blah. But I can't give you anything more than I've given you here. Next question, to answer some of the questions that were posed. Where are the rational or where are the design loads? Can anybody tell me? So this load has gone from 0 to about, what, 76, 78 kilonewtons. How much is the rational design load? Can anybody tell me? It's a test to successful failure. Oh, no, I'm afraid that person doesn't understand the question. It's a test to successful failure? No. What? So what are my design loads? Can anybody tell me, please? If my maximum load in the lab reach is 77, let's say, 78 or 76, what is my rational design loads? Can anybody tell me, please? Now you see the wheels are slowly starting to come off. The answer from person one is 76 kilonewtons. Anybody else? Just that, around 48. Anybody else? 75, 66. This sounds like the lotto, huh? 76, adjusted for factors. 64. Partial safety factors must be applied. I've got a headache from that. 22, 74. There seems to be a consensus building around 76. 12 millimeter displacement. Yes. Anybody else? Look at allowable deflections. No. Anybody else? All right. Let me help. Dependent on loading code. Okay. Right. So the steps to get to what are the rational design loads maximum would be to look at this reinforcement and use the code, whichever code is applicable, and back figure what is your what your loads are. Let me see if I've done that for you. Sorry, before we do that, let me show you the unload curve. So we've loaded and now we've unloaded. Can you see we've unloaded? Can anybody tell me if this beam has failed? Who says yes? This is a little bit more information, unloading information. Helps you? Yes. Plastic failure? No. Yes. 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 Consensus? Yes. Yes. Not return to initial form. Excellent. All right. Let's see what's on my next. So now I've calculated using the SANS 0100 or 100. Based on this reinforcement, I can produce for you the ultimate limit state and the serviceability limit state, assuming all the load coming on is live load. For your information, 10 minutes. Oh, I'm sorry, I'm going too slowly. Emmanuel, I think I'm going to speed up. All right, so this is ultimate limit state load, serviceability limit state, where has been one failed or has it? So where would you put your failure point now? Clearly it's somewhere here. Where would you put it? Anybody? $52-ish. You put it here, failure. All right. Anybody else? No. No. All right, so now let me release another piece of information on you. This is the place where the first flexural crack occurred, observable crack. It occurred here. Here's the first flexural crack that has occurred. Does that help you to determine? Where the first failure has occurred? Yes or no? Where has been one failed, or has it? Last chance. Okay, let's look at the answers. Answer 1, failure at first flexural crack. Clearly here it has failed. In reality, the beam has failed right here. As soon as the first flexural crack occurs, it has failed. It has failed. Let's look at a second answer. Failure at calculated serviceability limit state and ultimate limit states, and this will meet rational design loads. So the short answer is it's complex. The longer answer is, if you were just looking at material, this is the point of failure, first flexural crack. If you are to do rational design, these are my zones of interest where any load above this load would produce failure. So here is my failure point at the serviceability limit state. The ultimate limit state is boosted by the code. This is not failure. Failure starts to occur right here. Right, next question. I'm now going to take and I'm going to show you the photo right here. It looks like this. Can you see the flexural cracks? And the concrete has crushed here. Can you see it? Yes. So this is a beam in very bad shape. Question for you. How much load can the failed beam carry now? So if I were to start loading from here, can this beam carry any loading? Who says yes? Yes, yes, yes. All right. How much load can it carry? How much load do you think it can carry upon the second cycle? The beam is now tested from this state. In other words, concrete crushed, flexural cracks everywhere. We're at this point, if we were to load it again, minimal. Yes, it can, but probably not as much as before. How much? How much? How much can it carry? How much? Give it to me in kilonewtons. Let me give you a hint. How much load can this beam carry? It's totally destroyed by this cycle of load. 32. Yes, any load less than or equal to collapse load. What's my collapse load? What's my collapse? This has not collapsed. Sorry, this has not collapsed. The code is very interesting that it brackets my first crack between ULS and SLS. Very interesting, this. The code brackets it. Can you see it? There's been no collapse. It's still holding load. 66. Outside rational design? No, it's not outside rational design concepts. Not at all. Here's my second load cycle. See? Oh, it meets both the serviceability and the ultimate limit state. Can you see? It surpasses them. It's parallel. It's plastifying. Well above ultimate limit state. Even if failed, beam can carry load. Can you see that the beam upon the failed beam can carry load? It has not collapsed. So some people have already confused collapse with failure. Failure, I claim, is right at this point. If you want to be very much experimental based, failure occurs right at this point. Right at this point, first loading. In other words, no cracks visible if you want to follow the code. So the ultimate load reached here is roughly, this person was correct, 66 kilonewtons. Right, so the statement, but it works, no, it doesn't work. This still takes load. This still looks fine, even after this point. It still looks okay. You cannot tell with X-ray eyes if it has failed or not. Our understanding of failure is being questioned. Failed, but not collapsed. See this? It has failed, but it has not collapsed. All right. Now we can do the same experiment, but for under-reinforced. Under-reinforced produces similar results, but now the entire beam right from the start has failed because it does not meet rational design. It's under-reinforced. The reinforcement looks similar, but there's just a little bit less reinforcement in the tension zone. We cannot tell by looking at this beam a priori if it has failed, we cannot tell if it works or not. Beam still takes significant load after the first cycle. It appears to work, but does not work. In this one, does not work. So this one, I'll put the Jolly Roger here, which means dangerous, dangerous. It seems to work. Beam looks fine, but we've got no way of telling whether it will work or not work. We have no idea if it has failed or not failed. We have to go back to the office and do a rational design and see if it passes or not. That's what failure is. Failure is subtle. Failure cannot be seen by eye. But even under reinforced has not collapsed. This still holds load. And if I were to put a third load cycle, it would still produce load carrying capacity. And now, just to complete this slide set, I will ask you about shear. This is under reinforced. This beam is under reinforcing shear. Number 3 was under reinforcing shear. Here are the shear links. This is the spacing. Tensile reinforcement, good. Compressive reinforcement, good. Shear links spaced at 225 millimeters and violate the code. But the shear links, there's enough steel to satisfy the code. So it satisfies the shear link requirement, but does not satisfy the spacing requirement. My photo here, the rubbishy photo that some people claim has failed. It has not failed. It was taken right here at the unloaded state. The force deflection goes like so. Here's my serviceability limit state of shear, ultimate limit state of shear. The reason why I put danger is because shear cracks are much, much more dangerous than tensile or compressive rebar failures. So here we have it. Now the question is, does this work? Does this work? No, it does not work. We cannot see it doesn't work. That's why this Jolly Roger is here, skull and crossbones. This is not working. We can't tell that it works. It appears to be okay, but it isn't okay. Just because inside is wrongly spaced shear links. Now let's look at where does the first crack, shear crack occur? Does it occur in this zone, here somewhere? Does it occur in this zone, or does it occur in this zone? There's not enough time to ask you to vote, but let's see where it occurs. Aha, the first shear crack, first zone, no, it occurs here. That's where the first shear crack occurs. And notice how quickly afterwards the system fails. That's why this is dangerous. That's why this is dangerous. How much load can the beam take now? So we're at this point again. Here, can you see how bad the shear crack is? Sorry for the rubbishy photo. Can you see the shear crack? Can you see it? From the load to the bottom of the beam. The entire beam is cracked, eh? The entire beam is cracked. Major shear crack. Can you see it? I hope you can see it. Now, tell me, how much load can this beam take? Let's have a vote on this. This is important. Let's see who votes. How much load can this beam take? It has totally failed. And in fact, as I told you, it has failed not at this point, but right at the design stage. 1 minute to question and answer point. We'll have to go into this slot if a manual is to present. 0, zip, 0. Yes, all right. No, that's not the right answer. So now let's see how much load it can take. Here's the second loading sequence. Can you see? This was the start of the beam. It still went above the serviceability limit state shear. Right? Can you see that? We can say that, but it works. We can't make such statements by simple inspection. It appears to work, but it's dangerous. Shear cracks are dangerous. Even after failure, it still takes load. It has not collapsed. Failed, but not collapsed. Right. Should I be the only one that's talking, Emmanuel?
I think so.
All right. Just to conclude, Emmanuel's given up his time slot, ceded his time slot to me. Structural collapse is obvious. By now, you should understand it. Structural collapse is obvious. Failure is defined by the client and the structural engineer beforehand, a priori. Many types of failures exist. Structural failure is not obvious, cannot tell by a simple visual inspection. I think I've proven that to you. If structure does not pass rational design, it can be classified as failed. Notice the words that I use. If it does not pass design, it is can be classified as failed. The statement, but it works, is a fallacy. It is wrong and it is dangerous. The reason why things work in inverted commas is perhaps there are no loads on the structure. The second answer is, how does the observer know that it works without doing fundamental full-scale testing and review of the design? Rational design should lead to the structure not failing, and the root cause of structural failure cannot be determined using the building codes and standards. As I told you, buildings do not read structural codes or structural specifications. Structural engineers are not trained to do forensics and failure analysis. All right, that completes my presentation.